In our last two lectures, we focused on source and resistor combinations and saw how we could use those combinations to simplify some circuits. We're going to extend that a little bit further in this lecture and talk about two more circuit properties, voltage division and current division, that will greatly simplify some of the circuit analysis that you need to do. We will also introduce a new circuit element called the potentiometer, which is based upon voltage division. Let's talk about voltage division first. Suppose we have a whole bunch of resistors in series, R1 all the way up through Rn, and suppose we know the voltage across the whole series combination, V. Suppose that you want to find the voltage across a particular resistor, let's say R sub k. Let's call that voltage V sub k. It turns out that the voltage V sub k is just the ratio of that resistor R sub k divided by the sum of all the resistors multiplied by the applied voltage. Let's develop this equation and then see how it can be used. So from Ohm's law, we know that the voltage across R sub k, let's get rid of all this temporarily. From Ohm's law, we know that the voltage across R sub k is just its resistance times the current through it. So V sub k is R sub k times I sub k. But because all of these resistors are in series, they all share the same current. So rather than writing I sub k, we can just write I. But let's now look at the same circuit here. And instead of thinking of individual resistors, let's think about an equivalent resistance or equivalent, which is just the sum of the individual resistors. Turns out that its voltage, V, and its current, I, are related as follows. The current I from Ohm's law is just V over R equivalent. We can now take this expression here, plug it in here, to get that the voltage across R sub k, that's this voltage V sub k, is just R sub k times the total voltage V divided by R equivalent. And that gives us this final expression here. The voltage across the kth resistor is the ratio of its resistance over the total resistance times the applied voltage. So once again, V sub k is R sub k divided by the total resistance times the applied voltage. Basically, using voltage division allows you to skip these middle steps here and you can go right to the final answer. Let's look at a simple example. Suppose that we have 20 volts applied across 3 resistors in series. Let's make one of them 5 kilo ohms, one of them 2 kilo ohms, and one of them 3 kilo ohms. Suppose you want to determine the voltage across, let's say, the 2 kilo ohm resistor. So we want to determine this voltage here. Let's call this V sub 2. Turns out that what you could do is you could combine all the resistors in series, determine the current, and then multiply the current by that resistance to get that voltage. But it's simpler. We can just use voltage division. The voltage across that resistor is its resistance divided by the sum of the 3 resistances, which is 5 plus 3 plus 2, 10 kilo ohms, times the voltage across the entire series group, which is what, 20 volts. So basically, 2 over 10 is 1/5, 20 divided by 5 is 4 volts. So V2 is 4 volts. Likewise, if we wanted to find V3, the voltage across the third resistor, its voltage is going to be 3/10 of 20 volts, or 6 volts. Likewise, if we wanted to find the voltage across the first resistor, it's going to be 5/10 of 20 volts, or 10 volts. So what we see is the total voltage of 20 volts 10 volts is across the first resistor, 4 across the second, 6 across the third. They add up to 20 volts as expected. What we also see is that the larger the resistor, the larger the voltage, and the smaller the resistor, the smaller the voltage. Let's look at another example here. So here we want to determine what we call the voltage gain. Voltage gain is something we haven't talked about much yet, but it is a ratio of, let's say, an output voltage, in this case the voltage across the 6 ohm resistor here, divided by an applied voltage. So a gain is usually a ratio. Because it's a gain, it's going to be dimensionless. It's just going to be a number. The second thing we're asked in this problem is to find this current I. Let's look at the voltage gain first. What we're going to do is we're going to use the concept of voltage division to skip a couple steps. So what we see here is that we have a voltage-controlled voltage source over on the right here. So it's a voltage-controlled voltage source. So to find the voltage across this voltage source, we still need to find the voltage Vg, which is the voltage across this 1 kilo ohm resistor. We can use voltage division to find that, because the voltage across the 1 kilo ohm resistor is just 1/10 of Vs. So from voltage division, we know that Vg is just 1 over 1 plus 9 times Vs, or Vs over 10. Likewise, on the right-hand side, from voltage division again, we know that the voltage across this 6 kilo ohm resistor, V out, is just 6 over 6 plus 4 times 200 Vg. So we know that V naught, or V out, is 6 over 6 plus 4 times the applied voltage, which is this dependent voltage source, 200 Vg. We work out that math, we get 120 times Vg. We can now combine these two equations by basically sticking this into there to get that V naught, or V out, is 12 times Vs. So the gain, which is defined as the output over the input, is going to be 12. And notice it is dimensionless. I should point out that we could have come up with this answer without using voltage division. You could find some currents and then use Ohm's law to get it. Voltage division is just a shortcut. It's really nothing magical, but it's a way to skip a couple steps. If you know the voltage across a series group of resistors, you can then find the voltage across any subset of that using this voltage division property, this ratio. So the next question is find the current I. It really has nothing to do with voltage division, but it introduces another important point here. Let's define the current through this branch here. Let's call that I sub y. Let's call this current I sub x. So if we do KCL at that node, we get minus I plus I sub x plus I sub y is equal to 0. If we look at this node up here, though, this current is I sub y, this current is I sub x, so we get that minus IY minus IX is also equal to 0. If you combine these, what we see is that the current I has to be 0. This is an important result. We're going to see circuits that look like this a lot, not just in this course, but in future courses. This is a common model for certain amplifier circuits. So you basically have a loop on the left, another loop on the right, connected by a single wire. Turns out that there's no current flowing through that wire. That current is going to be 0. So you might ask, do you even need that wire then? If there's no current flowing through it, what's the purpose of the wire? The wire actually serves a very important purpose, because what it does is it forces this wire down here on the right to have the same voltage potential as a wire on the left. So although no current flows through that wire, it does guarantee that the voltage all along here is going to be the same, I just disappeared that. Current all along here is going to be the same and will be, in this case, 0 volts because we're connecting it to ground. Let's talk about current division now. So current division is the dual of voltage division. Suppose we have a whole bunch of resistors now in parallel. So R1, R2, all the way up to Rn, and I have them listed with their conductance G right now, and we'll see why in a minute. So all of these have the same voltage across them. Let's call it voltage V, but they have different currents, I1, I2, I3, all the way up to I sub n. What current division says is if we know the current flowing into this parallel combination of resistors, let's call that I, the current through the kth resistor is equal to the ratio of its conductance over the sum of all the conductances times the total current. So just like voltage division, the voltage across the kth resistor was its resistance over the sum of all the resistances times the total voltage. For current division, the current through the kth resistor is its conductance over the sum of all the conductances times the total current. Let's develop that, and we'll actually see that there's a slightly different version of this that we're going to use that uses resistances rather than conductances. From Ohm's law, we know that the current through the kth resistor is what? Its voltage divided by its resistance. So I sub k is V sub k over R sub k, or V sub k times G sub k. Because all of these resistors are in parallel, this voltage V sub k is the same for all of them, and we can just use this total voltage V. So I sub k is G sub k times V. But let's think about this equivalent circuit now. We can replace all of these resistors in parallel with a single resistor with an equivalent conductance, G equivalent, equal to G1 plus G2 plus G sub n. Of course, R equivalent is what? It's 1 over R1 plus 1 over R2 plus 1 over R sub n. This current I is that, this voltage V is that. From Ohm's law, what do we know? We know that the voltage V is equal to I over G equivalent, right? From Ohm's law, V equals I times R, or V equals I over G. We can plug this into here, and that gives us this expression here. So what we know then is that the current through the kth resistor, that's this current here, is equal to its conductance divided by the sum of all the conductances, G equivalent, times the total current. Because we work with resistors much more than conductors, an equivalent expression, and the one that we're going to use in practice, is replacing G sub k by 1 over R sub k. G equivalent is 1 over R1 plus 1 over R2 plus 1 over Rn. And all of that gets multiplied by I. So this is the alternate expression for current division using resistances rather than conductances. It's a little messier because we have all of these reciprocals, but basically what we see is that you take the reciprocal of the resistor of interest, divide it by the sum of all the reciprocals of all the resistances, and multiply that by the total current. Let's do a simple example here. Suppose we have 30 milliamps feeding 3 resistors in parallel. Let's have one of them be 2 kilo ohm, one of them be 6 kilo ohm, and one of them be 3 kilo ohm. What current division says is that this total current of 30 milliamps is going to distribute itself through the 3 resistors. Remember, with voltage division, the voltage distributes itself across all the resistors in series, and we saw that the larger resistor gets the larger voltage. In current division, because we have these reciprocals here, we're going to see that the smaller the resistor, the larger the current. If you remember the old adage, current follows the path of least resistance, that's exactly what current division says here. So if you use this equation to try to find that current, this current would be what? It'd be 1 over 2 over 1 over 2 plus 1 over 6 plus 1 over 3 times 30 milliamp. You work it out, you would get 15 milliamps. So this current is 15 milliamps. The current through the 6 kilo ohm resistor turns out would be 5 milliamps. And if you did the math, the current through the 3 kilo ohm resistor would be 10 milliamps. Note that the three currents, 15 plus 5 plus 10, do add up to 30. And also notice that the smallest resistor has the largest current, and the largest resistor has the smallest current. So current division and voltage division are very similar, but have sort of opposite properties there. Remember, current division is for resistors in parallel, voltage division is for resistors in series. Continuing with current division, it turns out that if you only have two resistors in parallel, the equation gets a little bit simpler. So we know, for example, that the current through R1 is its conductance over the sum of the two conductances times the total current I. G1, of course, is just 1 over R1. G equivalent is 1 over R1 plus 1 over R2. So let's take this expression here and multiply it by R1, R2 over R1 times R2. This is just 1, so we're just multiplying this expression by 1. But what happens now is this cancels with that. So in the numerator, we just get R2. In the denominator, R1 times R2 times 1 over R1 plus 1 over R2 gives us R2 plus R1, or R1 plus R2, and we get this expression. When you only have two resistors in parallel, the current through a given resistor is the other resistance over the sum of the two resistances. So you want to note that is the other resistance. You can always use a general equation, which is this one here, but if you can get by without doing these reciprocals, you can do that. The key thing to remember is if you want to find the current through R1, it is the other resistance R2 over R1 plus R2 times the total current I. Let's do an example with current division. Let's say we have a 5 milliamp source going through a 5 kilo ohm resistor, and then in parallel we have a 1 kilo ohm, a 4 kilo ohm, and a 5 kilo ohm resistor, and we're asked to find the current specifically through the 4 kilo ohm resistor. What we could do is combine all these resistors in parallel and in series to find the voltage drop and use Ohm's law to find that current, but instead we're going to use current division. Because we have this parallel combination of resistors, and we know the current flowing into that parallel combination, we can now use current division. I sub x is 1 over its resistance divided by 1 over 1,000 plus 1 over 4,000 plus 1 over 5,000 times the total current, 5 milliamps. You work out the math, you get 5/29 times 5 milliamps, or 25/29 of a milliamp. And that is the current through the 4 kilo ohm resistor. On your own, you can determine that the current through the 1 kilo ohm resistor is 100 over 29ths of a milliamp, and through the 5 kilo ohm resistor it is 20/29ths of a milliamp. Once again, note the 1 kilo ohm resistor, the smallest resistor, has the largest current. The 5 kilo ohm resistor has the smallest current, and the 4 kilo ohm resistor has a current that's in the middle. The other thing that you would note is that these three currents, that one, and that one, add up to 5 milliamps. So without doing a lot of work, we are able to find the current through the 4 kilo ohm resistor. One more point I want to make with this circuit, and that is with this resistor here. What we see is that this 5 kilo ohm resistor has no effect on the current through the other three resistors. Now that does not mean that this 5 kilo ohm resistor serves no purpose. It just doesn't show up in this equation at all. If you look at this equation here, nowhere does this 5 kilo ohm resistor come into play. And that is because it is in series with this current source. So this current source says that the current anywhere along this branch is going to be 5 milliamps, regardless of anything else that's in that branch. So the fact that there's a 5 kilo ohm resistor has no effect on the current. Since it has no effect on the current, which shows up here, it has no effect on the final current for Ix. But this 5 kilo ohm resistor does have an effect specifically on the power supplied by the 5 milliamp source. So the 5 kilo ohm resistor is going to have a voltage drop across it. That is going to increase the voltage across this 5 milliamp source, which increases the power delivered by the source. So we should add a comment here that this resistor will cause the 5 milliamp source to generate more power. So the bottom line, this 5 kilo ohm resistor here does not affect the currents through any of these three branches, but it does affect the voltage across the current source, which means it affects the power delivered by that current source. So it certainly has an effect on the circuit, but it does not have an effect on the other currents. Let's talk a little bit about some common mistakes when using voltage and current division. They seem like fairly simple equations, and they are, but it's very easy to make some mistakes. So look at the circuit here. You have a 10 volt source and three resistors, 4 ohm, 6 ohm, and 12 ohm. And suppose you want to find the voltage Vx. The first thing you might think is, I can use voltage division. Voltage Vx is this resistance, 6 over 6 plus 4 times 10. So you'd say Vx is equal to the ratio of 6 over 6 plus 4 times 10 volts, or 6 volts. That is wrong. The reason being is the 4 ohm and 6 ohm resistor are not in series. To use voltage division, you have to make sure that the resistors are definitely in series. The presence of this 12 ohm resistor here changes things. If you want to use voltage division, what you would have to do is first simplify the circuit a little bit. Keep the 4 ohm resistor here. Now, the 6 ohm and 12 ohm in parallel. Remember, R in parallel with R over 2 is R over 3. This becomes another 4 ohm resistance here. So now, the simplified circuit looks like this. Now we can apply voltage division. Vx would be 4 over 4 plus 4 times 10 volts. So we get 4 over 8 times 10 volts, or 5 volts. And this is the correct answer. So bottom line, you have to make sure that you're using resistors that are in series when you want to use voltage division. Another common mistake is with current division. You want to make sure to use all of the resistors that are present. So if you look at this circuit down here, we have a current source and a few different resistors. And you want to find Ix. Your first inclination would be, we have this 2 ohm and this 6 ohm resistor in parallel. You could say that Ix, using the shortcut, is the opposite resistance over the sum of the two resistances, 6 plus 2, times the applied current, 3 amps. And you would get 9/4 of an amp. Unfortunately, this is wrong. Although this 2 ohm and 6 ohm resistor are in parallel, they are not the only resistors in parallel. You have to make sure to use all of the ones that are in parallel or series. And it's very easy to forget this resistor because it's on the other side of the current source, but it is still in parallel. So the correct equation is Ix is equal to the conductance of the 2 ohm resistor, so it's 1 over 2, over 1 over 12 plus 1 over 2 plus 1 over 6 times 3 amps, or 2 amps. And this is the correct answer. Notice, because we have 3 resistors, we have to use a more complicated equation rather than the shortcut equation. The shortcut equation only works when you have just two resistors. In this next example, we are going to use a combination of voltage division and resistor combinations to find the voltage across a resistor in a circuit that is laid out in what is called a ladder network. A ladder network is a network which looks something like this. You can see why it's called a ladder network, because it's sort of shaped like a ladder. So in this particular circuit here, we are asked to find the voltage across this 3 ohm resistor here. There are many different ways you can solve this circuit. You could use the ad hoc approach. You could use nodal or mesh analysis, which we are going to be covering in a few lectures. But one approach you could use is a combination of voltage division and resistor combinations. And that's exactly what we're going to do. The first thing that we're going to do is collapse this network down to a point where we can use voltage division. And then we're going to go work backwards to find voltages throughout the circuit. So let's start by defining ground at this node down here. So the first thing we want to do is collapse the network. The way we're going to do that is we're going to recognize that this 9 ohm and 3 ohm resistor are in series, and that series combination is then in parallel with this 4 ohm resistor. So doing that, we have a 64 volt source, our 3 ohm resistor here, our 6 ohm resistor here, another 3 ohm resistor there. Then what we're going to do now is replace the 9 and 3 ohm resistor and the 4 ohm resistor with the equivalent resistance here, which is 3 ohms. Where does this come from? It's 9 plus 3 in series in parallel with 4. At this point, notice we've lost this variable V sub x. And normally I said you do not want to combine resistors if you lose that variable. Here is a situation where we're going to do it anyway, and we'll see how we can get back that V sub x even though we've combined this 3 ohm resistor with the 9 ohm resistor and the 4 ohm resistor. So at this point, we now need to do another layer of collapsing of the network. What we're going to do here is recognize that this 3 ohm resistor and this 3 ohm resistor are in series, and that series combination is now in parallel with that 6 ohm resistor. So we still have our 64 volt source. We still have this top 3 ohm resistor. Now, all of the circuit in pink, we're going to replace by its equivalent resistance. Its equivalent resistance is also going to be 3 ohms. Where does this come from? It is the 3 in series with 3, up here, 3 in series with 3, that is in parallel with 6. So 6 in parallel with 6 is 3 ohms. The reason we did this is we now have a circuit on the bottom with which we can use voltage division. Let's put ground there, let's put ground there. Let's define this voltage as V sub 1. That is a voltage across this 3 ohm resistor. This V1 we can find using voltage division. From voltage division, V1 is what? It's 3 over 3 plus 3 times 64 volts, or 32 volts. That means the voltage at this node is 32 volts, but this node is the same as this node up here. So that voltage is also 32 volts. This node is the same as that node up there, so the voltage at this node is also 32 volts. What we can now do is go to the second circuit, and we can use voltage division again to find the voltage across this 3 ohm resistor. Let's call this V2. Because we know the voltage at this point is 32 volts, this 3 ohm resistor and this 3 ohm resistor are in series. We have 32 volts across it. So V2 from voltage division is 3 over 3 plus 3 times 32 volts, or 16 volts. So the voltage at this node is 16 volts, but this node is the same as that one. So the voltage at this point is 16 volts. Finally, we can go back to the original circuit, and we can use voltage division a third time to find the voltage Vx. Because this 9 and 3 ohm resistor are in series, we know the voltage across that series combination is 16 volts. So we get our final equation that Vx is 3 over 3 plus 9 times 16 volts. You work out that math, you get 4 volts, which is our final answer. So once again, the way we solved this is we did 2 stages of collapsing the circuit, combining these 3 resistors into this one, then combining these 3 resistors into this one, and then we did 3 subsequent stages of voltage division. One to get V1, one to get V2, and finally to get Vx, our final answer. Once again, I should point out this is not the only way that we could have solved this circuit. We will see other ways in a couple lectures that might even be easier, but nevertheless, for ladder networks such as this one, this is a technique that works fairly well. At this point, we are now ready to introduce another new circuit element. The circuit elements we've looked at so far, the voltage and current sources and the resistors, are all 2-terminal devices. The potentiometer we're going to see is a 3-terminal device. In electronics, there are a couple 3-terminal devices that we will be using. The potentiometer is one that we use a lot. An op-amp is a 3-terminal device. We will use that an awful lot in this semester. In future semesters, in courses like EE 310, when you learn about transistors, transistors are also 3-terminal devices. By their very nature, 3-terminal devices are a little more complicated than 2-terminal devices because they do have more terminals, but they're very, very useful devices, and the potentiometer is no exception. So a potentiometer, which by the way we will abbreviate and call a pot most of the time, is nothing more than a resistor with 2 fixed terminals A and C, and then a movable wiper that is attached to a 3rd terminal, which we call B. This allows this resistor in this potentiometer to be broken up into 2 distinct parts: the resistance between A and B and the resistance between B and C. And this allows the pot to be used as a variable voltage divider, as we're going to see in some examples. So turns out that the total resistance between A and C is constant, and that is the value of the potentiometer. For example, if you have a 100K potentiometer, which is what we have in our labs, it means that this total resistance would be 100 kiloohms. Now, as far as this wiper blade that moves, it can be done a couple different ways. Some potentiometers have a dial with the screw slot, and you can move that, and that basically moves that wiper blade. And of course, the terminals would be A, B, and C. Other types of potentiometers have a knob that you can rotate. And once again, as you rotate that knob, it basically moves this middle wiper blade between the top and the bottom. So most potentiometers look like either this or that. You can also have potentiometers that look like slides. So basically you have a switch that just slides up and down, and that basically moves that wiper blade. Schematically, we will use this symbol for potentiometer, where of course this terminal is A, this terminal is C, and the one connected to the wiper blade with the arrow is B. You always need to have a value for the potentiometer. What that represents is the total resistance of that potentiometer. It turns out that the voltage between terminals B and C is a fraction of the voltage between the terminals A and C, and it depends upon the location of the wiper. So the resistance between B and C, we'll call it RBC, and let's also call the resistance between A and B RAB. So if you think about voltage division, suppose we know the total voltage across this potentiometer. Let's call it VAC. That's the voltage across the whole potentiometer. The voltage between B and C is then this resistance, RBC, over RBC plus RAB, all of that multiplied by this total voltage, VAC. But RAB plus RBC is a constant, and it's just the potentiometer value. So that means that the voltage between terminals B and C is just the resistance between terminals B and C divided by the pot value multiplied by the total voltage across the pot. Another way to think of it is you could have a variable x which varies between 0 and 1, think of that as a percentage. That is the percentage of the resistance that's between B and C. If the wiper blade is all the way on the bottom, it's going to be 0. If the wiper blade is at the top, it's going to be 1. So VBC is going to be X times R pot divided by R pot times VAC. And of course, these cancel, and you get this alternate expression that the voltage between terminals B and C is some proportion of the total voltage. But what's nice about this is we can adjust that manually by moving either the knob or by turning this dial here with a screwdriver. And so that allows you to, on the fly, change your voltage division in a circuit. We're going to see this is a very useful thing in lab. So let's look at a simple example first. So here we have a single potentiometer. It's a 10K potentiometer. It's going to have 3 terminals, A, B, which is this middle terminal, and C. We're going to connect C to ground. We're going to connect A to a 10-volt source. So first off, VB in this case is the same as VBC because C is connected to ground. So VB is the absolute voltage at terminal B with respect to ground, but because C is connected to ground, they are one and the same. So what is that going to be? The voltage at B is going to be a ratio of this resistance over the total resistance times the total voltage. So it's going to be whatever this resistance is divided by whatever the total resistance is times 10 volts. And of course the total resistance, we know, is 10 kiloohms. So let's think about the minimum and maximum. One extreme is when the wiper blade is all the way to the bottom. When the wiper blade is all the way down here, here's terminal A, there's B, and there's C, it's pretty easy to see that the minimum value of VB is just going to be 0 volts because that terminal is connected directly to ground that way. Likewise, the other extreme, if you move the knob to the other extreme, here's point B, there's A, and there's C, we get the maximum voltage at terminal B is just the voltage being applied once again because now VB is connected directly to the plus terminal of the 10-volt source. And by moving that knob, we can now move this wiper blade anywhere here, and we can get any voltage we want between 0 and 10 volts. For example, if we're at the 30% mark, we would get something like this. 10 volts, point A, point C, ground. It's a 10 kiloohm pot. And now let's say we're at the 30% mark. This resistance now would be 3 kiloohms. This resistance would be 7 kiloohms. And so VB now would be 3 over 3 plus 7 times 10 volts, or 3 volts. And once again, we could get any value between 0 and 10 volts just by moving the wiper blade. Let's look at a more complicated example here. So we still have this pot with terminals A, B, and C. But now we have 2 external resistors, a 10 kiloohm resistor and a 20 kiloohm resistor. The 10 kiloohm resistor is connected between terminal A and the plus terminal of the 10-volt source, and the 20 kiloohm resistor is connected between terminal C of the pot and ground. So the pot basically is this part here. So that's our pot. What we're going to see is that these 2 external resistors, this 10 kiloohm resistor and this 20 kiloohm resistor, are going to change the upper and lower limits. In the previous example, the upper limit was just the voltage source value, in this case 10 volts, and the lower limit was 0 volts. The presence of this 10 kilo ohm and 20 kilo ohm resistor are going to change both the upper and lower limit. So let's look at VB min in this case. We still have our 10 volt source. Now we have this external 10 kilo ohm resistor. We still have our 10K pot, and we have this external 20 kilo ohm resistor connected to ground. Now, when the wiper blade is all the way down, so C is this point here, there's A. Notice that VB no longer connects up to ground like it does in this example here. So now if we want to apply voltage division, we basically get 20K over 20 plus 10 plus 10 times 10 volts. So VB min, in this case, is 20 over 20 plus 10 plus 10 times 10 volts, or 5 volts. So the presence of this external resistor here keeps the minimum from going all the way down to 0. In this case, it's 5 volts. Likewise, if we want to calculate the maximum voltage at terminal B, we still have these two external resistors and our pot. Once again, 10 kilo ohm. This is our 10 kilo ohm pot. 20 kilo ohm. That's terminal A. That's terminal C. Now, maximum is when we're up there. There is B. So now, using voltage division, and let's draw ground. Using voltage division, the voltage at point B is this resistance from voltage division over this resistance times this voltage. So VB max is going to be 20 plus 10 over 20 plus 10 plus 10 times 10 volts. You work this math out, it's 7.5 volts. So we see that the minimum is no longer 0, the maximum is no longer 10, instead it's 5 volts and 7.5 volts. It turns out that you can pick these external resistors to get any range of voltage swing you want within the range of 0 volts to the power supply. So the external resistors allow you to pick the voltage range to be anywhere between 0 and the power supply. You're actually going to see this in lab. You will pick external resistors to get some pre-specified voltage range, and then you'll build it and then verify that you actually get that. Let's take this one step further. What happens now if you connect this potentiometer to a load? So in this example, let's attach it to a 20 kilo ohm load resistor. Is that going to change the voltage swing? If you just have the pot sitting there not connected to anything, we measured that the range would be from 5 volts to 7.5 volts. What we're going to see is the load is once again going to change our voltage division equation. So once again, let's look at the minimum case. In the minimum case, we have a 10 volt source. We still have our two external resistors and our pot, 10 kilo ohm or 10K pot, 20 kilo ohm. There's ground. Minimum situation is when B is there. There's point A, there's point C, there's B. But now we have an additional resistor here, 20 kilo ohm. And we're asked to find the voltage at point B. Once again, we can use voltage division. However, we can't just say it's 20 over 20 plus 10 plus 10 times 10 volts, because this 20K resistor is not in series with the 10K and the 10K. Instead, what we need to do is consider the fact that this 20K external resistor and the 20K load are in parallel. So VB min is going to be 20 in parallel with 20 over 20 in parallel with 20 plus 10 multiplied by 10 volts. You work that out, it's 3.33 volts. So once again, the presence of this 20 kilo ohm load is going to change this number there and there. Likewise, in the maximum case, we still have our 10 volt source, external resistor, pot, external resistor, and our load resistor connected to ground. Now, our pot wiper blade is connected up there to point A rather than to point C. $10K, 10K, 20K, 20K. And we once again want to find the voltage at point B with respect to ground. But now what we see is that this 10K pot resistance and this 20K external resistance are in series. That is all in parallel with this 20 kilo ohm load resistance. So now, to get VB max, the numerator is going to be 30K in parallel with 20K. So 30K in parallel with 20K, all over the same thing, plus the top 10 kilo ohm resistor multiplied by 10 volts. You work this math out, you get 12 over 22 times 10 volts, or 5.46 volts. So bottom line, when you add a load resistor, you have to take that into account when you do these voltage divisions. It turns out if this load resistor is much larger than these resistors here, it's going to have very little effect on the swing. And that's because if you have a large resistance in parallel with the small resistance, it's going to be approximately equal to the small resistance. So in this example, the load resistance was of the same order as these resistors here, and so it has a huge effect on the voltage swing. Instead of being 5 to 7.5 volts, it's 3.33 to 5.46. If you redid this problem and instead made this R load, let's say 20 mega ohms, that's much larger than 20 kilo ohms. What would happen then is 20 mega ohms in parallel with 20 kilo ohms is going to be approximately equal to 20 kilo ohms. It's only going to be a little bit smaller than 20 kilo ohms, and so the effect on this equation here and then down here would be minimal. Final comment about potentiometers is how are they used? Well, generally in a circuit they are used to control the intensity levels. Basically you can control a voltage anywhere in the circuit, which means you can use it to control the volume in a radio or TV, or in our final project we're going to use potentiometers as a volume control. Display brightness. Once again, you have a monitor, but you want to control the display brightness. Those knobs that you're pressing in there can very often be potentiometers that are basically limiting the voltage, which once again causes the display to be more dim or more bright. A dimmer switch on your wall switch, a little sliding switch on your wall switch to control the light, that is nothing more than a potentiometer. We're basically controlling the voltage that goes to the light bulb, which controls the brightness. Whenever you use an analog joystick, you are using potentiometers. Basically, the potentiometer is a position sensor. It basically helps you determine exactly where the joystick is, and that changes a voltage, and that's a signal that gets sent to the game console to basically let you know what movement you're doing. There are many other different places where potentiometers can be used. It's one of the most common circuit elements besides the basic things like voltage sources and resistors. We will use potentiometers extensively in this class, and you will use it in follow-up classes as well. The final example is when you want to use only two terminals of the potentiometer. If you use, let's say, terminals A and B, and ignore terminal C, the potentiometer can be used as a variable resistor. And we call that a rheostat. So basically what happens is if you're using just terminals A and B, by moving the wiper blade, you dictate how much of this total resistance you want to use. And so basically, if you have a 100 kilo ohm potentiometer and you're using terminals A and B, you can get a variable resistor that is some ratio of the total resistance. So you can turn a 100 kilo ohm potentiometer into any variable resistor in the range of 0 ohms up to 100 kilo ohms. And the idea here, once again, is we're not using the third terminal. So when you're using a potentiometer as a rheostat, you're turning it back into a two-terminal device. We will see sometimes that we like to use potentiometers as three-terminal devices, and there are other times where we want to use them as two-terminal devices where we're only using terminals A and B. By the way, if you only use terminals A and C, it serves absolutely no purpose because that is a fixed resistance and the potentiometer just acts like a regular resistor. Schematic symbol for a rheostat is just a resistor with an arrow through it. So basically this is telling us that we're using just terminals A and B. Technically, you could also use terminals B and C. It really doesn't matter whether you use A and B or B and C. But as I said before, you don't want to use terminals A and C because that doesn't give you any variability at all. One final comment about rheostats is it is generally good practice if you're using a potentiometer as a rheostat, where you're just using terminals A and B, to take terminal C and connect it to terminal B with a wire. This gives us added reliability. It basically takes this part of the resistance and shorts it out. Once again, gives us our variable resistance between A and B. It can be anywhere from 0 to the potentiometer value. It's not critical that you connect terminal C to B, but it's probably good practice to do so when you're using a potentiometer as a rheostat. Next class, we will talk about practical sources and another circuit simplification technique called source transformations, and we'll see how that can give us yet more ways to solve circuits. Anyway, have a good day.